Hey everybody, welcome back to Mr. A's geometry course. Today we're going over section 4.2 where we're going to learn how to reflect figures on the coordinate plane. Let's get into it. A reflection is another type of rigid transformation. Remember, this is a transformation that will create congruent figures just in different locations. So the side lengths will stay the same, the angle measures will stay the same. And this rigid transformation uses a line like a mirror, or we will learn this is called a line of symmetry or a line of reflection, that is going to flip a figure, right, the same distance to the other side of this line. Okay, and again, this is called the line of reflection. So as we look at this example to the right, again, sorry for my handwriting, this line here in the middle acts as our mirror line or our line of reflection. And we can see that all the points are equidistant to this line. So B and E are the same distance away, C and F are the same distance, A and D are the same distance. This is how a line of reflection works. We're just going to be using this on the coordinate plane. Certain types of reflections have very specific rules that can be followed where you can perform the reflection without even seeing a graph by just memorizing the function notation that occurs. So if you look at the graph to the right, we actually have a reflection over the x-axis. So remember, the x-axis would be this line, and hopefully you could tell all the points from the pre-image and the image are equidistant to the x-axis. Like A is 1 point above it, A prime is 1 point below it, and so on. And if you notice what happens with our coordinates, all of them have the same exact change. So notice from A to A prime that the x coordinate is still the same. They're both -2. But the y coordinate has gone from a +1 to a -1. And point B, the same thing happens. The x coordinates stay at +1. The b coordinates, though, go from +4 to -4. Sorry, the y coordinates, I meant to say that. The same thing happens for point C. The x's stay at +3, the y's go from +2 to -2. So how can we describe that change in function notation? Well, the x coordinate stayed the same, so it just remained x. But the y coordinate changed its sign. Now, function notation always starts with +x, +y, so to show a sign change, we would show a negative over here. So that +y becomes a -y. And this same change would explain how a negative would go from a positive, right? The sign just changes between them. That is the function notation. This happens for every reflection over the x-axis. So we can absolutely remember that function notation to perform a reflection. This says to plot A at 4, -2, and then reflect it over the x-axis. I could find the location of the image without even graphing by just remembering that function notation. The x will stay the same, my y will change signs. That means A prime needs to end up at +4, +2, because that y coordinate was -2 on our pre-image. Is going to change signs to our image. I'll also show you there how we can graph this by hand, right? And it's a pretty simple thing to do. So A is at +4, -2, that's right 4 down 2. That's right here, that's point A. I like to always highlight or just overly emphasize my line of reflection. In this case, that's the x-axis right there. And all we have to do is count how far away this point is from the line. And our distance here, when we count, will always be perpendicular, so we're just counting straight up. We can see that that's 1, 2 units from the line of reflection. So from that same location right there, we're gonna go 1, 2 units to the other side. And that's where A prime will be located, and that's exactly at +4, +2. That's how we perform reflections. We have to be equidistant to the other side of the line of reflection. In our next example, we're reflecting a segment. You notice it says in the x-axis instead of over the x-axis. That's just a different way of saying it, right? So I'm going to emphasize my x-axis here. And I can flip this figure 1 point at a time over this line of reflection. And again, I could do the function notation and just change my y coordinates, or I could do it by hand, which is what I'm going to show you here. So from point A, I'm going down until I hit this line of reflection. That's 1, 2, 3, 4 units away from that location right there. So A prime needs to also be 4 units away, just directly across to the other side of the line. So that's 1, 2, 3, 4, and A prime will end up right there. Again, we just do it 1 point at a time. So now I need to do this with point B. Notice though, B is going to flip above the line of reflection here. And it's how we do it, just 1 point at a time. It doesn't matter if we have points on different sides of the line of reflection. We just do it case by case. So B, I'm 1, 2, 3 units away. So B prime will be 1, 2, 3 units away from that same location, which will be right here at 2, 3. And again, if you were to investigate our coordinates here for A prime and B prime, they would be the same x coordinate, the y coordinates changing signs, just like our function notation says. We will notice a similar pattern every time we reflect over the y-axis. So the graph to the right shows a reflection of ABC over the y-axis to ABC prime. And as we investigate our coordinates, we can notice a change. Look at A and A prime. They both have 3 as y coordinates, but the x coordinates have different signs. Okay, looking at B and B prime. Again, the y coordinates are both 2, but our x coordinates are 5 and -5, so different signs. C and C prime, y coordinates are both -1, our x coordinates are different signs. So this time when we reflect over the y-axis, it's the x coordinate that changed its sign. So the function notation that will occur will be xy will become -xy. Y stays exactly the same, the x changes its sign. We can again perform this reflection here without even graphing if we remember that function notation rule. When we reflect in the y-axis, the x-coordinate will change its sign. So our point that we started with, +4, -2, will change the sign of that x-coordinate, and A prime will end up at -4, -2. Y-coordinate stays exactly the same. And again, we'll do this by hand just to confirm that this is correct. So +4, -2 is located right here. Our line of reflection is the y-axis this time, so that is this line right here. I drew that kind of bad. Let me redo that a little bit better, like so. And again, we're counting. This time we're counting horizontally till we get to this vertical line. That's 1, 2, 3, 4 units away from that same location. I'll go 1, 2, 3, 4 units to the other side. My flipped point, my reflection of point A would be there at -4, -2, just like we said it would. Next, we're asked to graph a segment. A is at 0, 3. That would be right there. B is at +5, -1. That's right here. There's our pre-image segment AB. We're reflecting over the y-axis, which we could do with our function notation rule by just changing our x-coordinate signs, right? We can also just do it by hand. We have a unique thing happening here in this example, which is that point A is on the y-axis. Whenever this occurs, the image will be in the same location. Because it's 0 units away from the line, its image will also be 0 units away from the line. So A prime will be in the exact same spot. B prime though, B is not on the line of reflection, so we're counting that. It's 1, 2, 3, 4, 5 units away. So we're gonna go 1, 2, 3, 4, 5 units away to the other side. There's the location of B prime. We're going to reflect a triangle now over the y-axis, and we can, in theory, do any shape. Doesn't matter how many vertices it has, right? We just do it 1 point at a time. Our y-axis, again, is this line right here. And recall that if a point is on the line of reflection, then its image is also on the line of reflection. So A is on the line there at 0, 1. So A prime will be in the same spot at 0, 1. C is on the line there at 0, 4, so C prime will be at the same exact location. And again, it's going to be point B that is actually going to flip over. That's 1, 2, 3, 4, 5 units away. 1, 2, 3, 4, 5 units to the other side will give us B prime right there. And again, we can connect all of those vertices for our image, ABC prime. Friendly reminder, your original shape is called the pre-image, that would be the green triangle. Your new shape is called the image, and we would call it prime, ABC prime. Next, we're going to learn how to reflect points in lines that are x equals a number. So like x equals 4, x equals -2, something like that. X equals a number is always a vertical line, which seems counterintuitive because we know the x-axis is horizontal. But x equals a number is always a vertical line. If you think about it, every point that's on this line over here of x equals 3, any point on that line would have an x coordinate of 3. For example, this point is 3, 0, that's 3, 1, this is 3, 2, this is 3, negative 1, and so on. Every x coordinate is 3, that's why the line is called x equals 3. The simple thing is to just memorize. X equal number is always vertical, okay? The number in question, the 3, you can also think of as where that line crosses the x-axis. So x equals 3 is a vertical line that crosses the x-axis at 3, right? And that's what this shows over here to the side. That's x equals 3. So in our first example here, we're going to plot that same point that we've been working with, positive 4, negative 2, so that's right 4, down 2. Right there, that's point A, and we're going to reflect it over the line x equals 1. So remember, this is a vertical line. It will cross the x-axis at positive 1. So our x-axis, we find positive 1, it's right there, and we draw a vertical line through it. That is x equals 1. That's the line we have to flip over. Now the reason I've been showing you how to perform these reflections by hand and not just using the function notation is for examples like this, where we do not have a specific rule because that number assigned here could be any number. It could be x equals 9, x equals 4, x equals negative 10. We have to be able to do this by hand because there's not a universal rule that applies here. So from A to our vertical line, we're counting 1, 2, 3 units. We're going to reflect the same distance, 1, 2, 3 to the other side. There at negative 2 is where A prime would be located. Again, we still see equidistant from the line of reflection even when we're not dealing with the x-axis or the y-axis. Next, we're going to reflect in y equals a number. So if x equals a number was always vertical, y equals a number is always horizontal. So again, kind of the opposite of the way the axes go. The y-axis is vertical, but y equals a number is a horizontal line. And that number in your equation will always be where the line crosses the y-axis. So when you look at our example here, this line is labeled as y equals negative 2. It's horizontal going left to right, and it's crossing the y-axis there at positive 2. This is what every y equals a line will do. And then as a friendly reminder, x equals a number will always be vertical. That line crosses the x-axis at negative 3. That's why it's called x equals negative 3. Again, to do y equals a number, we have a pre-image here, triangle ABC, that we're going to reflect over the line y equals 1. So again, we need to memorize y equals is a horizontal line. It'll cross the y-axis at that given number. So positive 1 is right there. A horizontal line through that point would look like that. And again, we're going to take one point at a time and we're going to flip it over this line. I'm just going to move left to right. So I see C is the furthest to the left. It's 1, 2 below the line. So its image will go 1, 2 above the line. And that'll give me C prime right there. A next, I'm going down now. 1, 2, 3, 4 down. I'm going to continue to go 1, 2, 3, 4 to the other side. There's A prime. Next we have B. Again, we're flipping to the opposite side, so we're going up now. 1, 2, 3, 4. Its image will be 1, 2, 3, 4 to the other side. Right there is B prime. Looks kind of funky because I'm just showing you that red just to show you how I count to get to these points. There is the location of my primes on my image. When we connect these, hopefully you can kind of see the symmetry that's happening between our figures and that given line of reflection. We have mirror images on either side of the line. It's okay for our figures to overlap like they do in this one. It's actually very common. Next up, we have these tricky lines, y equals x. These lines are tricky because they're diagonal. They're not vertical or horizontal, so flipping over them is not as intuitive as the other ones are. So the line y equals x is the line where the x coordinate and the y coordinate are the same for every point on that line. For example, that point right there is 1, 1, there's 2, 2, and 3, 3, and 4, 4, and negative 1, and negative 2, negative 2. You get the idea. The x and the y are the same at every point along that line. Now there is a rule here that applies. And to see the rule, we really want to look for points that don't have zeros as coordinates. So for example, if you look at point A on our pre-image, it started at negative 4, negative 2, And notice where A prime is. It's at -2, -4. Let's look at C. We started at -5, +1. C prime is at +1, -5. So what happened here? Our coordinates just flipped. Our x and our y just switched places. So that means the function notation for any transformation, any reflection over y equals x, I should say, just flips your x and y coordinates. So xy becomes yx. Simple as that. If you memorize that function notation, you can perform any reflection over y equals x without having to worry about what that line actually looks like. Okay? So y equals x is a line where all the x and y coordinates are the same value as I mentioned earlier. In our first example here, we're going to graph a segment AB and then reflect it over this is an error, I shouldn't have put the y-axis here, I should have put y equals x, because that's what we're practicing right now, over the line y equals x. And if we recall what we just learned about the function notation here, the x and y coordinates are just going to flip places. So I don't need to do anything complicated, I don't even need to draw the line of reflection on the graph. I can perform this without graphing at all. I can just switch my coordinates. So A was at 0, 3, A prime would be at 3, 0. Simple enough. B was at 5, -1, so B prime would be at -1, +5. Of course, I'm also going to show you how to do this by hand, just in case. So A is at 0, 3, right here, point A. B is at +5, -1, so write 5 down 1, there's point B. There's my pre-image. Now the line y equals x, again, it'll contain 0, 0, 1, 1, 2, 2, 3, 3, and so on. It'll look like this line right here. Notice how I hit all those intersections perfectly. 0, 0, 1, 1, 2, 2, 3, 3, and so on. Now the challenge in reflecting by hand over here is that we can't just go directly across the line because of the diagonal nature of the line. For example, for point A, we're not counting diagonally until we get to the line. We're still going to count horizontally or vertically until we get to the line. So let me go down here from point A. 1, 2, 3 units until I hit my line of reflection. Because this line is diagonal though, I'm not going to continue to go straight down to graph this reflection. Instead, I'm going to have to change directions and go to the right now to flip point A to the other side of this line. So from that same location right there, I'm changing directions now because my line is diagonal. I'm going right, 1, 2, 3. And that is where our A prime would be located at 3, 0, just like we determined over here. The same thing for point B. I can go to the left until I hit this line or up. I'll go up here first and go 1, 2, 3, 4, 5, 6 units away from the line. But again, I can't continue going up now because my line's diagonal. Now I'm gonna have to change directions and go to the left to flip over this line appropriately. So 1, 2, 3, 4, 5, 6. That is where my point B prime will be located. And again, I can connect those and we can see that kind of symmetric nature. That was a bad connecting segment, let me redo that. We can see that symmetric nature between our segments here. And again, our points do appear to be equidistant away from that line of reflection as they're supposed to be. I would say it's probably worth memorizing the function notation for these kind of reflections versus doing them by hand, because that diagonal nature can mess with some people visually with these problems. The last line we need to learn how to reflect over is the line y equals -x. So we have an example of what that line looks like to the right. This is similar to y equals x, but instead of rising from left to right, we're going to be falling from left to right, because this is a line where all of the x and y coordinates are going to be the same number, but they're going to have different signs. Meaning instead of the points being like 1, 1, and 2, 2, and so on, it would be like 1 and -1, and 2, -2, and so on. These points here are -1, +1, -2, +2, -3, +3, and so on for the line. Let's look at how the coordinates change for these points. Okay, if we investigate here, we can see that point B is located at -3, +2. And B prime is located at -2, +3. Okay, so what happened here? Our x and y changed, the numbers flipped again because I had a 3 first and a 2 second, and that flipped to give me 2 first and a 3 second. But another change happened here, which is that our signs are now different. That positive 2 became a negative 2. That negative 3 became a positive 3. This is the change that will always happen when you reflect over y equals negative x. Your x and y will flip, and the signs will change. So a positive x, positive y will become a negative y, negative x. In our next example here, we have a quadrilateral that we're going to reflect over the line y equals negative x. Again, if we determine the location of these points, we can just use our function notation, just memorize that I'm going to switch my x and my y, and I'm going to change the signs of both, and I can determine the locations for my image. I'm also going to show you by hand here, just in case. So again, this is what y equals negative x would look like, right there. Let me zoom in a little bit here so that we can tell visually what's going to be happening here. First thing I hope you notice is that point D is on the line. So remember, if a point's on the line, it's going to stay in the same place. So I already know that my D prime is going to be there in the same location. Let's look at the rest of our points. For a point like A, I can count down 1, 2, 3, 4 until I hit the line. And again, to flip this to the other side of a diagonal line, I cannot keep going down. I'm going to have to change and go this way. 1, 2, 3, 4. That ends up here. Again, if you were to investigate the coordinates, point A is at -1, +5 on our pre-image. A prime is at -5, +1. Again, that's just flipping the x and y and changing the signs. Point B here is located at 3, 3. So I know it's going to end up at -3, -3. And let's see how. By hand. 1, 2, 3, 4, 5, 6 units down. Now I need to go to the left. 1, 2, 3, 4, 5, 6 units. And there we are at -3, -3 for B prime. Right? Point C is located at +6, -4. So before I even do it by hand, if I switch those and change the signs, +6, -4 will become +4, -6. Let's see how it works by hand. If I go down 1, 2, I'm gonna go left now 1, 2, and that's right there, +4, -6. There's C prime. Here is my image of my quadrilateral at the reflection, and y equals -x. Again, probably more useful to memorize the function notation for this one instead of graphing by hand. While performing reflections needs to be the majority of your practice in this lesson, we will also have to describe reflections and any other transformation that we learn here in Unit 4. We have an example of a composition of transformations here. Remember, that's when more than one change happens on the same graph. In order to describe these, we're just going to do it one at a time. All right, so the first transformation, before I say that, we need to be able to identify our pre-image, our original figure, which would be the one that does not have apostrophes at its points, and that would be this blue triangle over here of QPR. Right, we are going from that to our first image, which would be the figure that only has one apostrophe by our points, which would be the pink one. So our first transformation here, we need to identify, and we've learned two types so far. We've learned translations, those are the slides, and reflections, which are the flips. And this does not appear to be a reflection. It doesn't look like my triangle has flipped over any kind of line. Instead, though, we can see that all of our points here have just been slid to the right a certain amount of units. That is a translation. So the first transformation that has occurred here is a translation, which we need to be able to describe. I'm going to do it in function notation here. So we started at xy, and then we can just count with our fingers how far we've slid. We're going to the right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units to get from Q to Q prime. Directly to the right, we're not going up or down at all. If you were to count for your other points, you would get that same distance of 10 units to the right. So xy becomes, going to the right 10 would be adding 10 to the x, and we're not going up or down at all, so the y coordinates would stay the same. So that's our first transformation. So translation, 10 to the right, so that'd be xy becomes x plus 10y. The second transformation, hopefully you can identify, is a flip. Even the arrow is kind of telling you, like, hey, there's some kind of funky thing that's happening here that gets my shape to the other side of this line of reflection. So hopefully you can identify the flip that has occurred there, making this a reflection. And some people will be very easily able to tell where the line of reflection is. And that would be the rule that we have to apply here. Just like we said how far we slid in the first transformation, if we say this is a reflection, we have to say what line we flipped over, or what the line of reflection is. And again, some people are visually going to be able to tell very easily. If you can't easily tell what the line of reflection is, then the midpoint formula is what's going to help you. Right? Because the line of reflection, remember, is equidistant from the points. It's halfway between the image and the pre-image. So if I were to do the midpoint formula with +6, -1, and +6, +1, I would get 6, 0. This point right here. If I did it with P prime and P double prime, I would get this point at 9, 0. If I did the midpoint formula with R prime and R double prime, I would get this point here at 4, 0. And then my line of reflection would just be the line that contains all of these points, which would be, which would be this line right here, which hopefully you can tell is the x-axis. So this is a reflection over the x-axis. And yes, you can also describe reflections with function notation. So you could say it's xy becomes x negative y because the y coordinates change signs. Our next example, we're describing the transformation here. We have our original figure is this one. It might be hard for you to see our parentheses in this. And this is the new figure down here. Our image is square ED FH prime. Right? And we had to determine how we've gotten from our pre-image to our image. A little bit harder to recognize that a reflection has occurred here. Right? If you think a reflection has occurred, then remember, you can find the midpoints between your pre-image and your image. And if there's a line connecting all of those, then you do indeed have a reflection occurring. For example, if I were to find the midpoint of -1, +3, and +3, -1, that would be here at 1, 1. If I were to find the midpoint of this point D and this D prime, that would be located here at 7, 7. If I were to do the same thing with my G's, ooh, they kind of messed up the letters that are involved here. They didn't put the same letters on this. They put an H down there instead of a G. It's supposed to be an H. But anyways, if I found the midpoints with these corresponding points, that would give me right here at -5, -5. And if I did the same thing with the F's, that'd be here at -7, -7, and then we can notice from that, there is a straight line that connects those. And if you notice all of our coordinates, there's 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Remember, that's the line y equals x. You can also kind of determine that from the coordinate pair that are given, -1, +3, and +3, -1. The x and y have just switched places. That only happens in a reflection over y equals x. So the type of transformation here is a reflection. The rule is a reflection over the line y equals x. One last reflection to describe here, all right? We take this triangle, it could flip to this position. There's definitely a reflection that has occurred. We just need to be able to determine the line that we reflected over, right? That's our rule for the reflection. Again, some people are going to be great with this visually, others not so. Remember, the midpoint formula can always help you out. If we found the midpoint between this point and this corresponding point here, right, that would be right there in the middle at -3, -2. If we found the midpoint for these rightmost points, it would be right here at -1, -2. If we found the midpoint for the most left points, it would be here at -4, -2. And then connecting all of those would give us our line of reflection right there. So from here, we just need to be able to determine what the name of this line is, all right? Helpful reminder, horizontal lines are always y equals a number. And then that number is just where that line crosses the y-axis. This crosses the y-axis at -2. Therefore, this is the line y equals -2. That's a reflection over the line y equals -2. That wraps up our lesson on reflections. We'll see you in the next one where we learn how to do rotations.